Good morning, everyone. So let's continue the discussion on PDAs. We designed some 5 to 6 PDAs with the given questions yesterday. So we'll continue from there and we'll talk about the difference between deterministic and non-deterministic PDAs. Okay. So whatever we designed till yesterday actually will fall under deterministic PDA. The reason is you saw we took configurations and either we accepted the strings or rejected the strings, and at no point of time for some input, some stack symbol and some state did we get confused what to do, right? That means there was only one action for every input, every stack symbol and from every state. So you had no confusion. We just followed it blindly. So if I am in this state, this is my input symbol and this is the stack symbol, I know what to do next. There's no confusion. There's only one path. That's why all the problems that we designed till yesterday will fall under deterministic PDA. But there are some problems which we couldn't solve using deterministic PDAs. So while discussing WCWR, I told you we cannot design deterministic PDA for WWR, correct? But this is also desired. Even length palindromes are also desired. Similarly, we couldn't, design, or we did not design a deterministic PDA for an equal number of A's and equal number of B's previously. So we can solve all these things by using non-deterministic PDAs. So what is a non-deterministic PDA? Like in your non-deterministic FSM, we had discussion about FSM also, right? Finite state machines. We had deterministic finite state machines and non-deterministic finite state machines, right? So the difference between them was, again, here only one course of action per input from a state, correct? However, in non-deterministic finite state machines, we had multiple paths to choose from. In the same manner, in deterministic, yesterday we saw we had only one course of action. But if we talk about non-deterministic PDAs, you will have multiple possibilities. For same, when you are in same state and on getting the same input also, you could do, and stack symbol also being same, right? You could do multiple transitions. So how did we show a non-deterministic finite state machine path? Similarly, you can show it even for PDA. Let us say just for an example, let us say there is something called as ABAB. We'll actually see the relevance of this after we design for equal number of A's and equal number of B's. But just to tell you what is non-determinism. So what do we do? If we had A power n, B power n, you already know that we pushed all A's, right? And we popped one A for each B encountered. But here, A and B are interleaved. They can come one after another also. So what we can do is we might choose to push it, or we may just, ignore an action. So there are basically multiple paths that are possible. So if I see here, don't worry about this, just see the example. This is on getting A itself as an input. Here we have consumed A and here we have not consumed anything, but we change the state from 1 to 2. Here we remain in same state, but we have consumed one input. Okay. Similarly, this can continue to any depth. Like here, you remain in state and you have consumed one symbol here and you pushed that B, whatever. And here you might change state, okay, and do something. Basically, don't bother about what's happening. All that you need to know is for each input symbol we might take multiple courses of actions, and that is called as NDF, non-deterministic PDA. Okay, so now the definition when we gave, no, for PDA, we said it has some tuples, correct? We said it has number of states, we said it has input symbols, we said it has a start symbol, it has a starting symbol, and it has a set of accepting symbols. So that this definition is general. If I have to convert this definition to deterministic PDA definition, this definition itself doesn't say anything about determinism. So it includes non-determinism also. Okay, it includes non-determinism. So it's okay if it's deterministic or non-deterministic, they will hold this. But if you want to fix this definition for deterministic PDA, then we'll have to add some clauses. Okay, we have to add some clauses, some restrictions. So obviously this will hold good. Along with that, you have to tell that this, I forgot to write delta, 6 tuples, 1, 2, 3, 4, 5, 6, yeah. Along with that, you have to tell if it's deterministic, then this should not contain any pair of transitions that competes with each other. Okay, so delta should not contain pairs of transitions that compete with each other. What is the meaning of this? The meaning is, let us say you are in a state called as Q1 and your input is A, and the start symbol is A. Just I'm writing. And the action for this, you'll say you will go to Q2. Okay. And let us say you are going to push that A on the top of A. And again in the same PDA, you might have something like that, you Q3 and pop. So here you can see for the same left hand side there are two actions. So if it is deterministic, then this is not a load. So that is the first clause. Okay. What about the second clause? Second clause says that if there is an accepting state, let us call Q as an accepting state. Okay. If Q is an accepting state, then you should not have any transition. What transition is not allowed? The transition something like this is not allowed. As you know, this is for acceptance, right? If Q is final state, that's what we are saying. Usually, if Q is final state, there is no input and there is nothing in stack. We accepted that, isn't it? So that's what we are saying. If we have this, then there should not be any transition like this for any P and for any A. Now, what is the meaning of this? The meaning of this is you should not be forced. In simple word, you should not be forced to choose between accepting, because so far for all our examples we saw this was accepting. So you should not be forced to choose between accepting, and this is continuing, isn't it? You are asking it to continue. So accepting and continuing. In simple words, this is the meaning. Okay. So the 6 tuple definition that we saw for PDA holds good for, I mean, it is required for both NPDA as well as deterministic PDA. Only difference is if you have asked it to be deterministic PDA, then you add two clauses. The clauses is for same input and same stack symbol from same state, you should not have multiple choices. There should not be transitions which can be chosen from. The second one is if you have an accepting configuration like q epsilon epsilon, where q is the accepting state, then for that don't have a transition, which means you should not be forced. Should I accept and stop or should I continue? This force should not be there, in which case we call it as a deterministic PDA. All right. Now, what we'll do is, of course, if we have ND non-deterministic PDA, there should be some advantages, correct? So, if you have non-deterministic PDA, that means you will have a PDA, you will design a PDA, right, which can have multiple moves. From a single configuration, which means what? We said this is not allowed for a deterministic PDA, isn't it? And we are saying that is allowed for a non-deterministic PDA. So from single transition, you can of course have multiple moves, okay, for non-deterministic PDA. So you can write a tree and for a configuration, and you can see each path from root to leaf. One thing is, one of such combinations, one such configuration will be accepted. Okay, so you can one possibility out of all the paths, one path will actually accept the string for which you have written. Okay, so now let us design some NPDAs. All right, for example, let us design how to write a PDA for palindrome, but this time it's an even palindrome. We designed a deterministic PDA for odd palindrome, WCWR. Now let us design the PDA for even palindrome. Okay. So here it's a language which has even length palindromes, means it will have W will also have A's and B's, and WR will also have A's and B's, and in reverse order of W. Correct? Now this is non-deterministic. Why? It's non-deterministic because we don't know when we reach middle. See, if it was WCWR, I knew when I reached the middle. C was the marker, isn't it? So you pushed everything which was there in W and then you popped if they are equal with WR. But here, how do I know what is middle? I don't know what is middle, right? In ABBA, how do I know what is middle? ABCBA, I know this and this is the middle. I mean, when you see through your eyes, in computer, it doesn't know what's coming, isn't it? It says only A. It doesn't know what's coming after that. So it doesn't know what is the middle input. So what it has to do is, before every character is read, like it reads A or B or B or A, etc. So before every character is read, it has two choices. Okay? Before every character or each character is read, it has two choices. That when you say two choices, we are talking about non-determinism. What are the choices that I have? One choice is guess that it's still not middle. That's one choice, correct? So if it's not in middle, then it will remain in the starting state and push. Similar to this, we pushed everything before the middle, isn't it? So guess it's not middle. If it's not middle, remain in starting state and push that symbol. Right? Or the second choice is guess that it is a middle, right? Assume it's middle. So what did we do when in the previous example, that is WCWR, once you reach the middle, we took the transition from starting state to final state, right? This is starting and this is final. So you took a transition on C when you got to final state. You consumed C, but you did not make any changes in the stack. In the last class, what we saw. But now you guess it's a middle. So you make now again transition to final state. But when you make transition to final state, now we don't have C to consume, right? So you make a transition on epsilon. So we know that in non-deterministic finite state machine also and non-deterministic PDA also, you can make transition on epsilon. Okay. And once you go to that F state, then all that you will do is popping. Even in WR, you pushed every element, you stayed in S, you got C, you made a transition to F. And once you reached F, so this part you are popping. The same thing you will do here also. When you are in S, whether it is A or B, you will push it. And whenever you assume that you have reached a middle, so you will reach the final state, and at the final state you are going to start popping. So how do I design a PDA for this? How do I design a PDA for this? So we are in starting state, right? And at each element, okay, at each element, if you get an A, it doesn't matter what is there in the stack, you are going to push A, right? Similarly, if you get a B, it doesn't matter what is there in the stack, you are going to push B. And this is for W part. All right. Then at some stage, you are going to assume you have reached a middle. So as I said, so there is no middle marker. You are only assuming it. So you are not going to make any change anywhere. You are just going to make a state transition to F state. And in F state, if you get an A on A, you are going to pop it. And if you get a B on B, you are going to pop it. Okay. And one such traversal will get you the final state. Or it will get you to the, instead of saying final state, it gets you to the final configuration. Okay. Final configuration, the accepting configuration, where there is nothing in the stack, nothing in the input, and you are in the accepting state. Okay. So let us see one configuration, and I'll do it only for this example because non-determinism means you have so many paths to choose, right? At each step you are assuming you are in the middle and also you are assuming you are not in the middle. So let me take a simple one, ABBA. And only for this example I'll do it, okay? From next NPDA designs, I'll not show you configurations. When you are free, you can try it out. So let us say from starting state, your input symbol is ABBA and nothing is there in the stack. Now I cannot show it like yesterday like this because there is no single path. I have to show it as a tree, right? So let me make a little space first to draw the tree. Okay. Let's draw the tree. Let's start from the starting state. Okay. And starting state here is S. The input is ABBA. Okay. And epsilon. Nothing is there in the stack. At this point, you can assume on seeing A, right, that you have reached the middle also, and also that you haven't reached the middle. So I'll take the left path, or assuming that I have reached the middle, and right path I can take, I haven't reached the middle. So if I hope this is clear, left I'll take, assumption is haven't reached middle. Okay. And from here onwards, at every stage, my right path is going to be an assumption that I have reached middle. All right. So if I haven't reached the middle, I'll consume this input, right? So what I'll be doing after consuming also, I'm in state A itself. I consumed it, right? And I pushed that A into stack. If I have reached the middle, then I'm going to make a change of state to F, correct? I'm going to make a change of state from here to here, but I'll make no changes to input. You can see that this is a simple transition. There is no change to input at all. Okay, this is one transition. Now next, if I take this thing, right? If I take this thing, S on B, and the stack symbol is A. So this you know that it's irrespective of whatever is there in the stack, right? So if I get B, I'm going to push B, right? So I'll remain in, again, two options. I have reached the middle, so I'll consume that B. Okay, I'll consume that B. So I'm left with BA. In my stack, I have BA. Also, if I assume I reach the middle, I'll be going to F with no changes, correct? With no changes. Now next, again here, two options. So think I have not reached the middle, in which case I'm going to push B. So it will become BBA. And here I'll assume it's reached the middle. So it will be F, there will be no changes, right? And I made a transition. Okay. Now here, I've assumed that I haven't reached the middle. So I'm at this stage, and after this I have no transition to do. Okay. So this is a dead state. This is a dead state. So it will stop over here. Now coming to this, FB on B, I have a transition, isn't it? Here see, pop it. When you are in F, A on A also pop, B on B also pop, correct? So FB on B, FB on B, again two choices. I'll assume haven't reached the middle, but there is no action, so it stops here. I'll assume I have reached the middle. So FB on B, oh sorry, only on S, two options. FB on B, I have to pop. So since I pop, I'm left with FA on A. Again, FA on A also pop. So I'm reaching this F epsilon epsilon, which is an accepting state, because F is accepting state and epsilon no input and epsilon nothing in stack symbol. So one path reached. We haven't written here, right? CFB on A, there is no transition. So it stops over here, correct? FB on A, no transition. Once you reach F, you have only transitions for A on A and B on B. So again here, F, A on epsilon, no transition. So it stops. So when you take multiple paths, at least one of the paths will take you to the final state if that PDA is designed to accept something like that. Otherwise, it will never go to final state. For example, if I take AB, we'll start with Starting state AB, nothing inside the stack. Again, assumption is you reached the final state and you did not reach the final state. So this is not reaching final, not reaching middle, and this is reaching middle. This is reaching middle, right? So if I don't reach middle, the assumption, then I'm going to push that, isn't it? Again here, if I assume this is not middle, I'm going to push B. And for this, there is no transition, so it stops. Here I assumed it as middle. If I assume it as middle, I am going to final state transition without making any changes. Again, there is no transition for F on BA. So I stop. Here also, when you assumed you reached the middle, you made a change of state from S to F without making any changes anywhere else. But again, F, A, epsilon, there is no transition. So none of the paths that we chose take us to final accepting configuration. So it rejects all of them. Okay. I'll again repeat this example once for you. The question was to design a PDA for even palindrome, WWR. So I don't know where the middle is, right? So since I do not know, I hope you are clear with that statement. I don't know where the middle is because the computer will see only one input at a time. Okay, and it doesn't know where the middle is because there is no marker. It doesn't know how many more characters will come, which was not like that in this case because we knew the middle, we recognized the middle when we came across the character C. Okay, so since we don't know when we reach middle, what we do is we use determinism, a non-determinism. Non-determinism means we take two paths. At every input, we make two choices. First, we'll guess it's not a middle, okay? And if it's not middle, we'll remain in the state and push it. Because the palindrome works like that, isn't it? So this much should be pushed, and for every matching symbol afterwards, you should pop. So every time you think it's not a middle, you remain in the same state and push. Or guess it's middle and make a transition to another state. Okay. But when you make the transition, make sure that nothing changes because it's just a transition. It's just a guess. So we designed PDA like this. We started with the S, right? So if you get A, it doesn't matter what is there in the stack, push it because you are assuming you are in the left side, W. Similarly, if you get B also, it doesn't matter what is there in the stack, you just push it. This is for the guess when you are assuming you are in the W part. At one character, you will assume that you have moved to the other side, WR part. So, you make a transition on epsilon. That is, you are not consuming anything, you are not making any changes to input or any changes to stack. They'll all remain as it is. Okay. Once you come to F, only pop option. That is, if your input is A, if your stack symbol is also A, pop it. Similarly, if your input is B and if your stack symbol is B, then you pop. Correct? So we took an example. And left side we thought we haven't reached middle. So you can see whenever we haven't reached middle, there is no change in the state. You are only consuming the input, pushing it into the stack. You consume that input, push it into the stack like that. But the right side you can see that, right side. So you assume that you have reached a middle. So you make a transition from S to F, correct? And after making the transition from S to F, there is no change that you will make to either stack contents or the input, okay? When will you make the change in F is only if you have like symbols. In input is also B and in stack it's also B. So in which case we are going to pop it, remove it, right? Consume B and pop B. So here also both input as well as stack symbol are A. So we'll pop it. And what is this? This is a accepting configuration. Why is it an accepting configuration? because F is accepting state. We drew this like this. And you consume the input and there is nothing in the stack. And you saw we had multiple paths here because of this guessing, and one path led to accepting. That is, if the string is acceptable by that machine. So this is not a palindrome. So you can see in all the three paths we traverse, none of them reach the final configuration. And so it will be rejected in all three paths. Okay. Now let's take one more design. Let's take one more design. Before I move on, I want to tell you one difference before I forget. One difference between PDA and regular FSM. Okay. See, if it's a regular FSM, every non-deterministic finite state machine can be converted to deterministic finite state machine. We have algorithms, right, to convert non-deterministic finite machine to deterministic finite machine. But that is not true for PDA. Okay. NPDA, every NPDA cannot be converted to deterministic PDA. Okay. There are many NPDAs. Okay. Many NPDAs for which there is no equivalent DPDA. I hope this is clear. If it's FSM, for every NDFSM, there is an equivalent DFSM, but that's not true in case of PDAs. Okay. Now let us take just one more example. All right. So equal number of A's and equal number of B's. So design PDA. So when they say PDA, we are going to design NPDA for this also. So for this language called as L, where W will have A or B star, right? And you have equal number of A's and equal number of B's. So number of A's in W is equal to the number of B's in W. Okay. So here we don't know if it's A power n, B power n, equal number of A's followed by equal number of B's. So I know when the B starts, after that A cannot come. So I can push all A's and I can pop for every B one A. But here it's not like that. We don't know in which order. Here, that's why non-determinism. Here we do not know in which order A's and B's will come. Okay. So one example is this. This is also okay. BBAA is also okay, equal number of A's and B's. ABBA is also equal number of A's and B's. Correct? So there are so many combinations like this. There is no one rule that you can see and say, okay, I can do this. I can push all this and I can pop all this. Right? So what to do? One, the only way is to count the number of characters that are not yet found their mate to use in the stack. Means for every A you will take an action for B. Here mate means for one A, one B. We'll make it as equal number of A's and B's. Correct? So here you have the only way is to count number of characters which haven't found the mate. For example, if I have something like this, 1, 2, 3, 4, okay. This also has equal number of A's and B's. So here I have 3 A's and 2 B's. So 1 A hasn't found a mate. Again, when I read this, 2 A's haven't found a mate. And then here, after you get that, every A has found their mate. Okay. So we use the stack here to count the number of characters which have not found their mate. So stack will sometimes count A, sometimes it will count B. So it will have everything, A's and B's. So it will count whatever it has seen more of. Okay. So how do I design a PDA for this? What does the PDA design involve for this? This machine is very non-deterministic. Okay. So let us say whenever it sees an A, the logic, whenever it sees A in input, it has two choices, correct? It can push it. So it will be right thing if I am counting A, means I have not found B's for this. Or, or you can attempt to pop B if it's there in the stack, correct? So every computation that will make some wrong guess will fail to accept, and one such configuration will be accepting it. So how do I design a PDA for this? Let us say I have a starting state. Why did I make that also as a final state? The reason is because no A's and no B's. If there are no A's and no B's, there are equal number of A's and B's, right? So first I said, if you have a A, it doesn't matter what is there in the stack, you push A. This is one option, right? Similarly, you get a B, doesn't matter what is there in the stack, you push the B. Next, this is the first thing, that is whenever you see an A in input, you can push or attempt to pop B. Or similarly, whenever you see B an input, you can push it or attempt to pop B. Okay. So, what's the equivalent for this A? This is when I am getting A and it doesn't matter what is there in the stack, I am trying to push A, trying to count A's, right? So, the other one, that is OR, it can try to pop, correct? So, if you have a and in stack there is a B, then pop it, right? Pop it. The second one is whenever there is a B in the input, it can either try to push it or it can pop a. So this is for pushing. If you see a B, it doesn't matter what is there in the stack, you just push it, right? Or if you see a B and there is an A in the stack, try to pop it. All right. So this is one way of designing. This is not the only way of designing. This is not the only way of designing. If there are different solutions that are coming to your mind, please do try it home, right? And please share the picture with me. I'll tell you whether your idea is correct or not. So I hope you understood how this works. Otherwise, let me just take. I said I'll not work it out, but let us just take. If you are in a state S and AB, so SA epsilon, you have an option, right? You can see here, when you get an A, if there is nothing in the stack, I can push it, right? So what will I do now? I'm going to push that A into the stack. Irrespective of what is there in the stack, I can push it. So I pushed it. Okay. Next, I have SB on A. SB on A. Now, SB on A, you can see one option is pop it. Or this also, when I write epsilon, it is irrespective of what is there, right? Irrespective of what is there. So B is there, A is there in the stack. So you can again push it. So I have two actions now. Okay. So I can either push that B, or I can pop this B and A, and in which case I am in this stage 2. Correct. So now next for this A on B, two options, right? You can see A on B you can pop, or A on anything you can push, correct? A on anything you can push. So let us take push option on the left hand side. So I pushed it. Or let me take a pop option. So if I take a pop option, so I've consumed A and popped B. So I'm left with this. Correct? Similarly here, again B on A, two options. I can pop or B on anything I can push. Correct? So S epsilon, if I chose push option, I am at this stage. And after this, I will fail because there is no transition for S, epsilon and B. So it will stop. Now if you come to the right side, I can pop B and consume B and pop A. So I am at this stage. Right? Again, this will stop because there is no configuration for this. Alright. Now coming to S, B on A. Two choices. One is push B and B on A you can also pop. Okay. Again this will stop because I have no configuration. This is the accepting configuration because S is also a final state, no input and nothing in the stack. So you can continue like this here also, but only one configuration will reach the acceptance state. Okay. And what should not be accepted? What should not be accepted? For that also I will draw one picture. What should not be accepted is something which does not have equal number of A's and equal number of B's, correct? So let me draw it here. Let us say we have ABA. This is not equal number of A's and B's. So SA on anything you have two options, that is push A or that's all. Next, SB on A you have two options. Either push it or you can pop B on A. So you will have this configuration. Correct? Now we are going to stop here because this doesn't continue. I do not have anything for A and epsilon. Okay? That is, we have, just a minute. A on epsilon we can push it, right? A on epsilon we can push it, but there is no configuration for this. That is epsilon A nowhere you can see. Epsilon A you can't see anywhere. So it stops here. Okay. What about this? A on B, two options, right? A on anything, push. A on B, pop. Two options. So let me take a push option over here. So I have pushed and let me take a pop option here. So I am at this. Again, same reason. There is no configuration, it stops. And there is no configuration for this also. Input being epsilon, there is no configuration, right? There is no transition functions for that configuration. So you can see all the paths have failed. So it will not accept. Okay. Let me stop here. Okay. And we'll solve one or two more problems and see how to reduce non-determinism, because non-determinism is not preferable. We talked about it when we studied the DFSM also, and that is NDFSM also. That's why we converted that non-deterministic finite state machine into deterministic finite state machine, because non-determinism is not preferred that much. So as we saw in this case, I told you earlier that for every non-deterministic finite state machine, there is no equivalent DPDA. So there will be some machines which cannot be converted into deterministic. But however, we can reduce the non-determinism. We can reduce the non-determinism, and we'll see that also in the next class. Okay.